So let's discuss about more about the current electricity chapter. Okay, so this is going to be session 3rd for this, which we will be discussing. Are you able to see the screen? Let me share you the screen, I think, first. Right?
Yeah.
Okay, so let me share the screen. So is it visible now? Right? Check it's visible or not.
Yeah,
Okay,
it is.
so ICSE Class 10th chapter is current, electricity, and this is going to be the session 3rd for this. Current, electricity, 3rd session. So in the previous session we discussed about what? We discussed about resistance, we discussed about Ohm's law, okay, and in Ohm's law we found that V upon I is equal to constant, remember, which is equal to the resistance. What is resistance? Resistance is the obstruction in the path of the electrons, or you can also say obstruction in the path of the current, okay, that is called as the resistance. All right, we actually discussed about the Ohm's law, which said that if the physical conditions like temperature, pressure, etc. of a conductor remains constant, then the current flowing across the conductor is directly proportional to the potential difference applied across the ends of the conductor. Okay. Now we will be seeing the graph of Ohm's law. We will be starting with the heading graph of Ohm's law. Okay, so there is an experiment which you have to conduct for plotting this graph. Okay, understood?
Yeah.
So for that, what you have to do? You have to do the experimental verification of the Ohm's law, and you have to draw the graph. Okay, how you will draw the graph and how will the graph come out to be? Let me tell you. Okay, the graph will be like this. So here what you are going to do, you are going to plot the voltage and current. So when you will be plotting the voltage and current graph, it is always going to come linear like this. Okay, it is always going to come linear like this. Clear? Basically I am drawing from my digital pen, that's the reason why I haven't shown it as perfect as it should be, but it is always going to come linear, the graph of Ohm's law. Clear?
Okay.
So what is it? Graph of Ohm's law is, it's basically linear, and this value is what? This is resistance. Clear? Understood? So if
Yeah.
I will find the slope of this, okay, slope of this graph, slope is what? Quantity on y-axis upon quantity on x-axis. So slope equals to V upon I, and this slope will give me what? Resistance. Clear? The slope of this graph is going to give me the resistance. Clear? Understood? So slope is, always remember, the formula for slope is quantity on y-axis, upon quantity on x-axis. I will help you do some numericals on this slope, and with the help of that you will be able to understand. Okay, so this is VI graph. What is this? This is VI graph. So it's always going to come linear. Similarly, another thing can also happen. What? We can take I on x-axis and V on y-axis, V on x-axis and I on y-axis. Clear? Now what I can do here, again I will plot the relationship, so it is always going to come linear. like this. Clear? It's always going to come
Yeah.
linear like this. Okay, so VI or IV graph, whatever you plot, it's always going to come linear. But here, if you will find the slope, okay, if you will find the slope is quantity on y-axis and so quantity on x-axis. So this slope is going to be what? I upon V, and it is equals to 1 upon R. And this 1 upon R is nothing but the inverse of the resistance, which is actually equal to what? Conductance, denoted by the capital G. Okay, this capital G, it is called as the conductance, the reciprocal of
Okay.
resistance. Okay, the opposite of resistance is conductance. Clear?
Mm-hmm.
The opposite of that is conductance. Clear what I'm trying to do here?
Okay.
Okay,
Yeah.
so this is IV graph. I hope everything is clear to you. Now how we will plot this IV graph, let me tell you this. Very easy, we can easily plot this graph. Okay, so there is a thing which is called as the experimental verification of Ohm's law. So we will be doing the experimental verification of Ohm's law. Clear?
Yeah.
Ohm's law. So how I am going to do the experimental verification? Really very easy, no problem with that. Experimental verification of Ohm's law. So for that I will be needing some devices, some electrical devices to form the circuit for Ohm's law. So remember, always remember that the Ohm's law circuit will be like this. See, first of all I will connect a battery. Okay, I will have a battery here. Okay,
Okay.
and let us connect this to a rheostat. Now what is a rheostat? Can you tell me what is a rheostat?
I don't know.
Rheostat is basically the one of the device which provides the variable resistance. Okay, you don't know the value of the resistance, but it provides the resistance. Clear? That is the rheostat. Okay, I will also show you how does that rheostat looks like. Okay, don't worry. So this is rheostat. Okay, and then this rheostat, it is connected to the switch K. Okay, an ammeter A. Ammeter, remember, it measures the current. Okay, so for measuring the current, because we are plotting the relationship between the voltage and the current. Okay, so I will be needing the voltmeter and ammeter both to measure the current and the voltage. So I have the ammeter which is connected in series. Remember, ammeter is always connected in series. So what does the ammeter do? Ammeter, it measures the current. Clear? What it does? It
Yeah.
measures the
Measures the
current. Okay, and it is always connected in series. Remember this, very important point. Always connected in series. You will later understand why it is connected in series when I will be telling you the parallel combination and the series combination. Okay, clear about this?
Yeah.
Now
Yeah.
this whole circuit will have a known resistance R. We actually know the value of this resistance, so I will take the known resistance R. Okay, and known resistance means I can also take the resistance box. Now what is the resistance box? Resistance box also provide the resistor, just like this rheostat, RH rheostat, but rheostat provides the variable resistor, whereas it provides the variable resistance. Okay, it provides variable resistance. However, this resistance box, it provides the known resistance. You know the value. Okay, clear? So instead of the resistance box, they have actually connected the known resistance R. but in some of the circuits you will also find the resistance box which is connected, and parallel to this resistance box there is a voltmeter which is connected. Voltmeter is always connected in parallel, remember this. Okay, parallel to this voltmeter is connected. Clear? I hope it is clear to you.
Your voice is like really glitchy. So.
No. Is my voice fine now?
Yeah, right now.
Okay, okay. So voltmeter, remember that voltmeter is always connected in series and it is used to measure the voltage. Okay? Clear? Now this is the switch K. So what will happen? Obviously this battery, what it will do? It will send the current I. Okay, because current always starts from the positive terminal. This bigger line is the positive terminal of the battery and this is the negative terminal of the battery. Clear? Okay, so this current will flow. This current will flow. It will flow. Now whenever there is a parallel combination, current divides. Okay, that's the reason why I am saying that voltmeter, it is connected in what? Parallel to this resistance R. Okay, and this current will go here and this current will be measured by the ammeter as well. Okay, now what we will do actually here, we know this value R, we know this value. Okay, now I will slide the bar of the rheostat. Now how does this rheostat looks like? Let me tell you. Rheostat looks like this. I am going to share this rheostat.
I can't hear you.
Wait a minute, I am sending you. Okay, let me show you the rheostat.
Hello?
Okay, can you connect back?
Okay.
Connect back. Okay, now can you hear me?
Yeah.
Okay, so basically as you can see, what I will do, I will actually slide the bar of this rheostat, okay, to increase or decrease the resistance. Why rheostat?
Okay.
Because rheostat controls the value of current. Okay, because when we will be increasing the resistance, current is going to decrease. When we will be decreasing the resistance, current is going to increase, right?
Yeah.
Okay, so what will happen, we will slide the bar of this rheostat, okay, because it provides the variable resistance and it will control the flow of current. Okay, that's why. So how does that rheostat looks like? Let me show to you. See, this rheostat looks like this. There is a bar here. Are you able to see this?
Yeah.
When we slide this bar, the resistance changes. We can increase or decrease the resistance. However, we don't know the fixed value of the resistance, like how much resistance we are actually changing. Okay,
Okay.
understood? But
Yeah.
whenever the current, so whenever we will be sliding this bar, okay, let me show you. Whenever we will be sliding the bar of this rheostat which you are seeing here, okay, the value of the current will change. So ammeter will note down that reading, show that reading to us, and the voltmeter will be also showing its own reading. Okay, like what will be the change in the potential difference across the ends of this wire, which is R. Okay,
I can't hear you again. I can't hear you.
okay, I think there is a problem with your internet connection, right?
I think mine's fine because it's showing full bar.
Mine is also showing full network. Wait a minute.
I'm not sure.
Okay. Now can you hear me?
Yeah, I can hear you.
Wait a minute. Can you hear me now? Is it fine? Hello, is it fine now?
I can hear you.
Okay.
Yeah.
So now what will happen? This rheostat, it will increase or decrease the current. Okay, it will
Yeah.
control the flow of current. Okay, and the same will happen with this voltage. Okay, so the value of the current will be measured by the ammeter, and the value of the voltage will be measured by the voltmeter. Okay, by changing the by sliding the bar of the rheostat. So we will measure the different values of current and the corresponding voltage of the value to that current. Okay, and then after that we will plot the VI graph. So this is how we will plot the VI graph from this. Clear what we actually do? And
Yeah.
when we will plot the VI graph, the result is always going to come like this. The graph is always going to come linear.
Okay.
Okay,
Yeah.
the graph is always going to come linear. I hope everything is clear to you now.
Yeah.
Okay, so in your lab there will be the experiment of Ohm's law. Kindly conduct that experiment with extreme responsibility, because that experiment is going to teach you lot of things. Okay, experiment is always different from theory. You learn a lot from experiments. Clear? Shall we move on?
Yeah.
Okay, really very good. Now after that, since we have discussed the Ohm's law, okay, so rest of the procedure you can read from the book, because it will take time to write the whole procedure. The whole procedure is given in your book. I have explained to you everything about Ohm's law and about the experimental verification of Ohm's law. Okay, so you can read the whole procedure from your book. Clear?
Yeah.
Because the whole of the experiment is given, so I'm not going to make you write the notes on the experimental part, because experimental part is given in your book first of all, and that will also be done in your lab. That's why I'm not doing it here. Okay,
Yeah. Okay.
now there are some kinds of things which are called as the ohmic resistors and the non-ohmic resistors. Let me tell you about that as well. So let us discuss about the ohmic resistors. So this was second heading, and heading number third, that is the ohmic resistors and non-ohmic resistors. And non-ohmic resistors. Clear?
Yeah.
Ohmic resistors and non-ohmic resistors. Now what do I mean by the ohmic resistors? Ohmic resistors means, okay, the which obey the Ohm's law. The conductors which obey the Ohm's law, those are called as the ohmic resistors. Clear?
Okay. Yeah.
Alright, so I am writing here conductors which obey the Ohm's law. Okay, which means the graph is going to come linear for these. Okay,
Okay.
always going V and I graph is always going to come linear. Clear about this?
Yeah.
Okay, so all metallic conductors, these they follow the Ohm's law. Okay, clear about this? So if we will plot the graph between V and I or I and V, the graph is always going to come linear. V upon I is always going to be constant for all values of V or I. Clear?
Yeah.
Now what are non-ohmic resistors, by the way? Okay, so non-ohmic resistors are the conductors which does not obey the Ohm's law. Okay, they do not obey the Ohm's law. And mostly non-ohmic resistors are either the semiconductors, okay, are the semiconductors. So we can write the semiconductors which does not obey the Ohm's law, because Ohm's law, that is followed to some extent by the semiconductors, but after that it does not follow, only for some devices, but for most of the devices they do not follow Ohm's law. Okay, so we can write the devices, okay, or we can say the ones which do not follow Ohm's law. Ohm's law. What is the example? Examples are semiconductors, most of the semiconductors, okay, semiconductors. So if you will plot the VI graph, voltage and current graph, in semiconductors, there are different kinds of semiconductors. The voltage and current graph is going to be very unique. Okay, I will show you how it looks like. Okay, now in a similar way, so this is for semiconductors. Okay, then the types include semiconductors. LED is also made from semiconductors, right?
Okay.
LED, light emitting diode, it's a kind of a semiconductor, to be honest, because it's actually made from the material which is a semiconductor. Junction diode, just remember the names, because it is not going to come in your syllabus like what is diode and all of that. That is the concept of the higher class. Junction diode, transistor, etc. Okay, so these are what? These are the non-ohmic resistors. Clear?
Yes.
So if you will plot the graph between the non-ohmic resistors, V and I graph of the non-ohmic resistors, okay, it's going to come like this. Okay, so this is V, this is I, not linear, it's going to come like this. Clear?
Yes.
Okay, some of the semiconductors, their graph VI relationships is like this as well, like this. Okay, now
Yeah.
so this is VI graph. Clear? So look, it is not linear actually. So this is for the non-ohmic resistors. Clear? This is the
Yeah.
relationship. Non-ohmic resistors.
Yeah.
Let me show you few of the graphs of VI graphs for the semiconductors. Okay, let me show you here. So I am writing, you can see, because if I will draw from the pen, it's not going to come accurate. Okay,
Okay.
of semiconductors. See, it looks like this. See, isn't it? See, so
Yeah.
the VI relationship is going to be different. You will study this graph in higher class. What is leakage current, what is forward current, what is breakdown voltage, all of that you will study in the higher class. Okay, I hope it is clear to you. All right, so now let's move ahead. So this is actually see, this is what happens when you draw with the pen. Okay, it's going to come like this when you draw with the pen. This is what happens. See, like this. Okay, now clear what are non-ohmic resistors?
Yep.
Okay, so now what is the difference between the ohmic and the non-ohmic resistors? I am going to write here for you. So just copy that down and then we will be doing the next heading. Okay, so between ohmic and non-ohmic resistors. Are you able to see me right?
Yeah.
So let us discuss each of these in detail. All right. So when I'm talking about the ohmic and the non-ohmic resistances, so what is the main difference? Tell me. I just told you.
Oh yeah.
Number one, it obeys the Ohm's law.
Resistors.
Yes.
Yeah.
Number one, ohmic resistors. Ohmic
And
resistors,
always have a
yeah, obeys the Ohm's law. While non-ohmic resistors does not. Clear? Okay, which means V upon I relationship will be followed. Okay, so I can write ohmic resistors obey the Ohm's law. So in bracket you can write that is V upon I is equals to constant, while non-ohmic resistors does not follow Ohm's law. Okay,
Yeah.
clear about this? Now, so number second is because they follow the Ohm's law, so the graph of plotted between voltage and current or vice versa is always linear. Yes or no?
Yeah.
While for non-ohmic resistors, what will happen? Tell me. While for non-ohmic resistors,
they are not linear.
yeah, they are not linear. Okay, they are the VI characteristics are non-linear. Clear? Number third point. What is the number third point? Tell me. Slope will be same, right? Because it is linear, so slope will be same for all values of V and I.
Yeah.
So the slope of VI graph for ohmic resistors, okay, are going to be what? Same at all values of V or I. Clear? Whereas for non-ohmic resistors, what will happen?
They're not all the same.
Yeah, slope of VI graph is not same. Clear about this?
Yep.
Okay, so these are some of the differences between the ohmic and the non-ohmic resistors. Okay, now I am going to tell you very important relationship now, okay, which is really very important. Clear? That is the resistivity. But for discussing the resistivity, I need to first tell you the factors on which the resistance depends. Okay, so what we are going to discuss? We are going to discuss about the factors on which resistance depends. Factors on which resistance of a conductor depends. Resistance of a conductor depends. Very important heading. Okay. Clear? Factors on which resistance of a conductor depends. So can you guess what are the factors on which the resistance of a conductor depends? Tell me.
Um, the rheostat.
No. See, resistance of a conductor depends upon the length. Okay?
Okay.
Length. Okay? It is directly proportional to length. Resistance is directly resistance of a conductor is directly proportional to its length. Okay?
Okay.
Is directly proportional to the length of the conductor. Clear? These things are observed experimentally. Alright, resistance of a conductor is directly proportional to the length. Length L of a conductor, let us say L, and resistance is capital R, let us say, okay, of a conductor. Which means, what do I mean by this? This means that R is directly proportional to length. Larger will be the length, more will be the resistance. Yes or no?
Yeah,
less will be the length, less will be the resistance. More will be the length, more will be the resistance. Clear? Equation number 1. Now let's talk about second thing. On what factor the resistance depends? Tell me. Upon the area of cross section. Area of cross section. Cross section of the conductor. Clear?
Yeah.
Of the conductor. Area of cross section of the conductor. So always remember, resistance is inversely proportional to the area of cross section of the conductor. Clear?
Okay.
Cross section of the conductor. Clear about this?
Yeah.
So I can write R is inversely proportional to area. Let us say area is A. So R is inversely proportional to area.
Yeah.
It's equation number 2. Okay. Now third thing on which the resistance of a conductor depends. Can you tell me what is that? Tell me. What is that?
I don't know.
You don't know? Okay, that's fine. It depends upon the nature of the material. Okay?
Okay.
It depends upon the nature of the material. So, third, like if you will take insulator, it is obviously it is going to have very high resistance. Yes or no? If you will take wood, can current flow through the wood? No. Current cannot flow through the wood because it is an insulator. Insulator provides very high resistance. That's why. Okay. So it also depends upon the nature of the material. Nature of the material. Okay. Number 4, it also depends upon the temperature of the conductor. Okay, it depends upon what? Temperature of the conductor. Conductor. What do I mean by this? By this I mean that whenever there will be increase in the temperature, okay, so electrons will the speed of the electrons will increase, right? There will be more movement of the electrons and there will be more collisions with the positive ions, so resistance will also increase. So What happens when the temperature is increased? So when the temperature of a conductor increases, very important point I am writing here, when the temperature of the conductor increases, so what will happen? Tell me. I just told you.
Then the resistance will also.
Yeah, the resistance also increases. Clear?
Yeah.
And why does this happen? Also increases. Why does this happen? Because on increasing the temperature, I am writing here very important point. On increasing the temperature, what will happen? The random motion of electrons will increase. The random motion of electrons
will increase.
will increase. Will increase, due to which there will be more collisions. Clear? More collisions. More collisions are going to be there. Very important point. Okay, due to which there will be more collisions. Okay, with the what? With the electrons. Okay, and the positive ions.
Yeah.
With the other electrons. Right, let us write other as well. Other electrons and positive ions.
And the positive ions.
Yes, and positive ions, resulting in the increase of resistance. Okay, in the increase of resistance. Clear?
Increase of resistance.
Very important point.
Yeah.
I hope it is clear to you. So temperature, it also depends upon the temperature. Okay, so now area of cross section we have discussed. After that we found two things, that it depends upon the length and it depends upon the area of cross section. Now what we will do, let us combine equations 1 and 2. Combining equations 1 and 2. So when we will combine equations 1 and 2, what is going to be our answer? So let's combine. R directly proportional to L upon A. Yes or no?
Yeah.
Because R was directly proportional to length and inversely proportional to area of cross section. So this will be R directly proportional to L upon A. And this will be equation number 3rd. Now when I will remove the sign of proportionality, what will come? Tell me. Tell me what is going to come.
1 by L.
There will be constant which will come, just like in case of resistance. When V was directly proportional to I, we remove the sign constant and the resistance come with which was the constant. This constant was also called as the resistance, right?
Resistance. Yeah.
So whenever we remove the sign of proportionality, there is a constant which comes out. Okay, clear? So here there will be also constant. So R equals to that constant is called as the rho. Rho L by A. Rho L by A. And what is rho? Rho. This is called as the rho. Okay, RHO, rho. Clear?
Okay.
This is our relation. R equals to rho L by A. And where? What is this rho? Rho is also called as the resistivity. Rho is the resistivity, and the second name is resistivity. And what is the second name? Or specific resistance. This is the second name of it. Or specific resistance of the conductor. Clear? Or you can also say wire, because we are considering wire as the conductor. Okay? Clear about this? What I have done here? So this is called as the rho. Rho is what?
Okay.
Specific resistance or resistivity.
Specific resistance. Yeah.
So now I can define what is specific resistance. I can define it easily. What is specific resistance? Just let us write the heading: specific resistance. Specific means we will be talking about the specific resistance. Specific means particular. We will be considering the particular area, and we will be considering the resistance of that area. That is the specific resistance. Okay?
Okay.
Let me tell you how. Specific resistance. How? Let me tell you. Or it is also called as, the second name is what? Tell me.
The resistivity.
Very good. Resistivity. And denoted by the symbol rho.
Rho.
Okay. So what is resistivity or specific resistance? Let me tell you. Rho, formula is R equals to rho L by A. We discussed about this formula. R equals to rho L upon A. This was the formula. Right?
Yeah.
So in terms of rho, I can write rho equals to RA upon L. Yes or no?
Yeah.
So let us do one thing. Let L equals to 1 meter. Let us say L equals to 1 meter. Okay, we are taking this length as 1 meter. Okay, and area of cross section as 1 meter square. Okay, area of cross section as 1 meter square. Clear? We will take everything as unity. So then what will happen? Tell me. When A is equal to 1 meter square, L is also equal to 1 meter, what will happen? Tell me. Try to think out of the box.
The resistivity. It would just be resistance.
Obviously, this, when this will become 1, this will become 1, they will cancel out each other, and rho will be equal to R.
Resistance.
Then which means specific resistance is equal to only resistance. Okay.
Yeah.
So we can easily define the resistivity now. Therefore, how we can define resistivity? I am writing here. Okay.
Resistance.
Resistivity or specific resistance, same thing. How we can define? Okay. How we can define? We can define like this: specific resistance, or also called as the resistivity. Clear? A specific resistance or resistivity of a material is the resistance of a wire, resistance of the conductor, or you can also say wire, because we are considering wire here. Okay, wire of that material.
Yeah.
Conductor material having unit means 1, having unit length and unit area of cross section. Unit area of cross section. Clear? This is how you will define a specific resistance or resistivity. Okay? Clear?
Yeah.
Okay, so larger the value of the resistivity, more will be the resistance. More resistance it will offer. Clear? So it is different for different substances. Understood?
Yeah.
Clear about this? Okay. So basically, specific resistance also depends upon the nature of the material. If your material is metal like silver, copper, aluminium, lead, tungsten, iron, tin, whatever, okay, specific resistance is always going to be low, very low. Whereas if they are the insulators, for insulators specific resistivity, specific resistance or resistivity is always going to be very high. Okay, for example, let me give you the example. There is also a table which is given in your book. You can consult the book for more of the examples on specific resistivity. So specific resistance of some substances, it is given at 20 degree centigrade. So for silver specific resistance is equal to how much? For silver it is equal to 1.63 into 10 to the power minus 8 ohm meter. Ohm meter is the unit of the specific resistance. Clear? Or resistivity. While for the resistance it is always equal to ohm. So for silver we have rho equals to 1.63 into 10 to the power minus 8 ohm meter. Whereas for glass, or let us say wood is an insulator. For wood it is going to be really very high. For wood it is going to be 10 to the power 8 to 10 to the power 11 ohm meter. See how much high it is. Yes or no?
Yeah.
Okay, so for insulators it is going to be really very high. So this is for metals. Metals is a conductor. Okay, metals, or we can say conductors. Whereas wood is a non-metal, right? Insulator. There is another category which is also called as the semiconductors. For semiconductors it is not going, neither going to be really very low nor going to be really very high, in between. Okay, like for example graphite is a semiconductor. Germanium, let me give you the example, one example which is a semiconductor, that is germanium. Germanium is what? Semiconductor. So for it is not going to be really very high. It is going to be 0.6 into 10 to the power minus 5 ohm meter. See, it's not going to be very high. See, silver has very less. Look, 10 to the power minus 8. Okay, wood has very high, 11. It's in positive, very high resistivity. Germanium, not very high, not very low. Okay, in between the insulator and the conductor. Okay, so it's what? Semiconductor. So for more examples you can consider your book. Okay.
Yeah.
Now what are the factors on which the resistivity depends? Let us discuss that as well. Okay. What are the factors on which the specific resistance or the resistivity depends? Heading number 5th, factors on which resistivity or specific resistance depends. So what are the factors? Can you tell me?
Of resistance.
Yes.
Would it be the same?
Yeah. Tell me. Don't worry. If you will be wrong, I am here to correct you. Tell me.
Length.
Don't consider length here. We are just talking about specific resistance, which means we are just considering the particular area and length, which means unit area and unit length only. So we are not considering the whole length there. That's why we will not consider the length here. Okay.
Okay.
Now tell me.
Temperature.
Very good. Temperature. So what about the temperature? It increases or decreases?
Increases.
Okay, so there are two cases. Okay, so first I am going to write the temperature. Okay, so very first thing, very important thing. Okay, just take the note of this, it's going to very important. Okay, so the specific resistance of the specific resistance for metals, I am talking for metals first of all. Okay, so for that of a substance. Okay, what happens of a substance depend on its temperature, depends on its temperature. So for metals, which means for conductors, usually for metals it increases. When we are talking about the metals, it increases with increase in temperature, just like the resistance used to increase, okay, with increase in temperature. Whereas okay, it decreases with the increase in temperature for semiconductors or alloys, okay. It
Okay.
decreases with increase in what? Temperature.
Temperature.
For what? Tell me.
Which we need.
Semiconductors
Oh.
And
Okay.
various alloys. Clear?
Yeah.
And what are the examples of alloys? It includes
Semiconductor.
constantan, manganese. These are what? These are the alloys. Clear?
Okay.
Not manganese, that is the metal. Manganin. Okay, my mistake. Manganin. Manganese, it's a metal. It's atomic number 25, manganese. Okay. Alright, even for the insulators as well, it actually decreases with increase in temperature. Clear?
Yeah.
I hope everything is clear to you.
Yeah.
Now, another factor on which it depends, on the nature of the material. Okay,
Okay.
am I right or not?
Yeah.
Just like the resistance used to depends upon what? The nature of the material.
Yeah.
The specific resistance depends upon the nature of the material. That is, it is very low for metals, that is conductors, okay, conductors,
Okay.
and very high for insulators, which are non-metals. Okay,
Okay.
clear? You can give the examples and well, I have already given you the example. Example is this. Okay, for silver, like what is the specific resistivity? 1.16 to 10 to the power minus 8, very low.
Yeah.
Understood? For wood it is really very high, 10 to the power 11, positive. For germanium, it's a semiconductor, is not going to be really very low or very high like the insulator. Understood?
Yeah.
Clear? So this is it for today, and it was really a very nice session with you. One more thing, SI unit of resistivity, I have already discussed that, but let me solve this for you. SI unit of resistivity or specific resistance, or we can say specific resistance. So what will be the SI unit? Tell me.
Okay. I'm assuming the same as
Ohm.
resistance.
Ohm meter, right? Why?
Okay.
Because rho equals to RA upon L. Okay. So unit of rho will be what? Unit of rho, this will be equal to unit of R
Yeah.
into unit of A, SI unit of A upon SI unit of L.
Okay.
So what it will be? Your unit of R is what? Ohm. Unit of area is what? Meter square. And
Meter
unit of
square,
length is
yeah.
meter. So meter and meter will cancel, and we will have ohm meter as the unit. Clear?
Yeah.
Okay. So this is it for today. We will meet in the next session, and in the next session we will be discussing some more about the conductivity. Okay, and we will be solving
Okay.
some of the numericals as well, and we will be discussing about the resistances in series and resistances in parallel. Okay, very important.
Yeah.
All right.
Alright.
Okay, this chapter is really very long, because like it will take around 10 to 12 sessions to complete this chapter, to be very honest. Okay, because lot of things are there in this chapter. It's a very long chapter here. Okay, numericals are also there, then I have to do electrical energy and power, then there is a separate portion for EMF, separate numericals for all of these. That's why it's a long chapter as compared to the others. All right.
Yeah.
Okay, so don't forget to revise, otherwise you will forget the things. Okay, understood?
Yeah.
All right,
Yeah.
so we will meet in the next class.